Uh, well, welcome everybody, and today it's a great pleasure to have Giuseppe Mussardo giving a talk here. Giuseppe is an old friend of the Institute. He likes to come here, and this is his first visit since the beginning of the pandemics. And well, he enjoys heat of Brazil, and we met him with some here. So he's a researcher at SISSA in Trieste, and he's working in statistical field theory and integrable models and other applications of mathematical physics. Particularly, he is very fond of prime numbers. So today he will talk about experimental work and about realization of these prime numbers. So please, Giuseppe.
Okay, thanks, Dimitri, for the nice introduction. So, good morning. So, since it's a summertime, let me give a summer seminar. So, will be kind of entertainment. I hope you will enjoy. But you will see there is some, indeed, deep question going on. So, I'm going to report about some recent work and been done together with Donatella Cassettari, who is in St. Andrews in Scotland, with the experimental side of the group. Andrea Trombettoni, who is my colleague in Trieste, theoretical physics as me. So, what is about? Well, you should know that recently there has been an increasing interest for the profound and engaging links discovered between number theory and physics. Now, number theory is a very, special status in mathematics because it's probably the only subject which is the farthest possible to physics. The reason is very simple and also historical, if you want. The point is that physics, since the start, say since Newton, is based on some continuity. So, I mean, you want to follow the path of a trajectory. So, you're going to have continuous time, you're going to have differential equations. So, differential equation are at the heart of physics, especially because we believe in the continuity of space and time. Now, number theory, on the other hand, intrinsically, the DNA is based, on the other hand, of some kind of discreteness. So, some kind of the basic property you find are, recursive equation, or you find combinatorics, or you find really discrete numbers. So this is the reason why somehow the two subjects, number theory and physics, has always been detached. There is an however, though. And the however is indeed the discreteness I just was telling you. Now, recently, there has been discovered many connections between the subject, which make the field particularly interesting to look at. First of all, there has been some work done on the long-standing problem of the Riemann hypothesis, that you know is about the location of zeros of a function, which is this one, the Riemann zeta function. In the complex plane of the variable s, Riemann stated that all these zeros should align along the real part equal 1/2. Now, the understanding of this problem has discovered some really profound and deep relation with the random walk. I have no time now to dig, I'm just telling you what is about, in the sense that the spreading of the random walk, which goes like square root of n, so n to 1/2, the 1/2 can be related to the real part of the zero of this function through a very simple mathematical tools, which is the Mellin transformation. Anyway, I have no time now. I don't want, this is not the topic of my talk. I'm just enlightening that physics can indeed bring some light and let us understanding in a very simple way why the zeros of this function align along the real part equal 1/2. But there are more. For instance, all the work on modular functions, which is once again a great and noble subject of physics, And the light, recent time, also other long-standing problem like the entropy of black hole. So counting the number of states of black hole can be related really to some very nice piece of mathematics coming directly from number theory. Now there are many, but I just want to give you an idea what's going on. Now today, on the other hand, I'm focusing on a fingerprint, say, of statistical mechanics, which is spectrum. I told you before that the detaching of number theory from physics is due to the fact that physics usually is based on some continuity and number theory is based on discreteness. Now we know that on the other hand, the reality is much more complex and rich, and in particular, quantum mechanics tell us that things are discrete. So there might be a direct link then between the two subjects. So energy, of course, participates in emission of light, and the fact that each time that you see an element or you see substances like here, the light emitted by the sun, you find some discrete line means that what you are observing refer to some discrete set of numbers. Therefore, there is a natural questions. The natural questions are, if I give you an arithmetic sequence, does exist a quantum mechanics system which has this sequence as a spectrum? So I want to reverse the order of the things. Usually, we study a system, helium, we find certain spectrum, and then we use as a fingerprint of helium each time that we see that line. As I said, I want to reverse the story. I give you some sequence, and I would like to know whether exists an atom, quotation, that has this sequence as a spectrum. And associated to it, there is a related question, namely, let me assume that this sequence I associate to an Hamiltonian, say an energy. Of course, I can use other observables, but just for convenience, let's from now on stick to the point that I'm adding to some Hamiltonian which support such spectrum. Now, is this Hamiltonian unique? Okay, so in this seminar, my attention will be focused on one-dimensional Hamiltonian of the most familiar form, so quadratic part and the momentum and some potential, okay? Or, if you like, equivalently, I'm looking for three diagonal Hamiltonians. So this is the matrix of the Hamiltonian, infinitely many. Okay, here is cut it, but it's supposed to be infinitely many, with some potential along the diagonal and some -1 along the next neighborhood diagonal. Now, this kind of diagonal is nothing else than the discretization of the previous one, but somehow it's nice to have in mind because this can be a priori easily realized in terms of some, some device, some blocks, where you allow hopping, say, of the electrons and some potential that refer to each individual box, okay? So this is the kind of Hamiltonian operator I'm looking for in order to set up the spectrum I would like to have, okay? Okay, now imagine that you are fond of Fibonacci. Now Fibonacci is a series of number, is a sequence of number generated by these recursive equations with initial condition f0 equal 1, f1 equal 1. And once you give this initial condition, this equation give for you all the rest, okay? Now, these numbers are interesting for many, many reasons. In more recent time, they enter also explicit realizations of the so-called topological quantum computations and the way how the Hilbert space increase along a sequence of gates. Now, these numbers can also be associated to the nth power of these matrices. So if you take the nth power of these matrices, the corresponding element A, B, C, D, just line up as the Fibonacci numbers. And this is particularly convenient to illustrate what is called a geometrical paradox. Indeed, you see, if I take the determinant of this equation left and right, here I have differences, quadratic difference of the Fibonacci, but here I have -1 to the n. Now this is indeed endless source of jokes. For instance, you take this square, which is 8 by 8. 8 is a Fibonacci numbers. I divide in this way, and then I move these shapes in this other one, obtaining from 64, 65. Okay? So if this were made by gold layer, I could become endless rich. Okay? Now I can fool you even more if I use other Fibonacci numbers. Because as I said, the difference between next consecutive product of Fibonacci and the square of it, so this is the 8 square, and this is 5 times 13, you see, 8, 5, 13. The difference is -1, which is at the origin of these things. Now, this linear recursive equation allows us to compute exactly what is the nth Fibonacci numbers, and is given by this formula, which is called Binet formula. You see that the Fibonacci number grows like the golden ratio. This number is very special in number theory. It's called golden ratio because it's associated to the shape of the Parthenon and the love of Greek for symmetry, to the nth power. This guy is subleading term. So the Fibonacci numbers grows exponentially, grows very, very fast. Hence, does not exist a Fibonacci atom. Namely, the fact that this sequence goes so fast forbidden us to have an Hamiltonian as the one I was presenting, which support this spectrum. Now, the reason, as I say, is the sequence grows too fast, and similarly, with the same kind of argument, you can exclude that you can write down a quantum Schrödinger Hamiltonian, which, for instance, has the spectrum of the so-called Mersenne numbers. Because once again, these are exponentially growth of the so-called perfect numbers. Perfect numbers are those whose sum of divisors is the number itself. So, for instance, 6, divisor is 1, 2, 3, the sum is 6. The next one is 28. 1, 2, 4, 7, 14. If you sum up, it's 28. Now, these numbers, which are nice and interesting, however, from quantum mechanics point of view, grows too fast. Indeed, you can easily prove that for the Hamiltonian I gave you, there is a bound on the growth of eigenvalues. Namely, for any Hamiltonian of this form, the sequence of energy level must always satisfy this inequality. As far as you have infinite sequence. If you have finite, there is no problem. But insist to create an Hamiltonian which has unbounded spectrum, the only numbers that you can engineering in this way must satisfy this bound. Okay. Now this is very easy to prove. I can give you a very shorthand argument. You know that in quantum mechanics, if you have a potential, let's say, which has certain spectrum, if I make it steeper, the eigenvalues increase. Okay. So you can ask yourself, what is the potential which has the larger possible increases for unit length? Is the infinite wells. Because in a short time, you just get infinite. And such potential, the eigenvalues goes n square. Okay? So you cannot find any potential which grows faster than the infinite well, and therefore the eigenvalues cannot grow more than n square. So you can try, let's say, with exponential of exponential as potential, you always find n square. Okay? But this can be proved. I'm just giving you an argument for that. Okay, so we know now which set of numbers I can, in principle, accommodate into a quantum mechanics problem. So let me consider now one of the most interesting, though elusive, set of numbers, which are the primes. Now, the primes are identified by a sieve. There is no other way. Namely, in number theory, a sieve is when you give a certain criteria to put in the basket the number you want. Okay? So the Eratosthenes sieve, which is due to Eratosthenes already 1,000 years ago, has a very, very graphical interpretation. Imagine that you put all the natural number one in a row, along the things, and you give them a slope. Okay? So the primes are those which can arrive to the very end of the slope. And operatively, the story goes like this. You start from 2. Definitely 2 is not divisible by anyone by 2 himself, so you put in the basket of prime. But once you have done this, you have to put a hole each row which is multiple of 2. So this means that when I start with 4, let's say, this ball immediately hit this hole and go down, is not a prime. Okay? Now, you go, once you have put 2 in the basket, you go to the next one. The next one is 3, so it goes through all the way because it's not divisible by 2 and it's the only divisible by 3. At this point, you erase each 3 times, so 6, 9, 12, and so on and so forth. So this means a 9th, when you repeat the same exercise, the 9th ball just hit the hole and is not a prime. Okay? So this is a way of selecting, screening the primes from the natural numbers. So prime, as we know, are those numbers which are only divisible by 1 and themselves. Now, you must know that there isn't a closed formula for the prime. Contrary to Fibonacci. Fibonacci, I can give you the nth Fibonacci number in a closed formula. But if you ask me what is the 100 primes, I really have to count. Okay? Nevertheless, there is a very nice scaling law of the prime, which I'm going to prove it in a minute, which is this. So the nth prime, roughly speaking, scale like n log n. And then there is stunning conclusions. There must exist a quantum Hamiltonian that support the prime as eigenvalues. Because this guy satisfy the bound. Hence, the prime number, craziest as can they be, can be eigenvalues over Schrödinger equations. Okay? Now, let me bring you now in a little detour on the property of the primes, because it's fun. It's really an amazing set of numbers. I told you that there is no way of telling what is the nth prime, but there is a way of counting them, which is kind of is the inverse problem. Okay? Namely, let me denote it, as has been done historically, by pi over x, that function which count the number of prime less or equal to x. Now, this function, of course, is a step function. It increases by 1 each time that it a new prime. And of course, the closed formula I was looking for prime is the inverse of this function. What I mean is, if you see when this function hit the value 10, well, the 10th prime is exactly what is associated to this jump. So morally, how to say, that to get the nth prime, you should solve these inverse equations. Now, this is inherently a step function because it increased by 1 each one it hit a prime, but it goes without saying that your sensitivity to the jump is question of scale. Because if I increase the scale of these functions, so imagine that now I plot in more and more and more numbers, well, the jump becomes less and less violent. And asymptotically, if I'm interested really in a large astronomical, large number, this you can assume to be a continuous function. A continuous function that has fascinated Gauss since then, since he was young. So Gauss say, can I compute this function? Okay. Now, the way Gauss got it, actually what I'm going to present is not really the argument of Gauss, but somehow we can rephrase this, what Gauss could have thought about it, goes like this. And this led to the so-called prime number theorem. The argument is absolutely fascinating. This is the result of Gauss. Gauss says this continuous function I was talking about can be approximated by the so-called logarithmic integral. Logarithmic integral is this function, dt log of t between 1 and x, which essentially goes like x log x. Why so? So as I said, what I'm going to present is not the proof of Gauss, but in the spirit of Gauss. The proof is, let's say, a la physicist. Not rigorous, but exact, I would say. So let me assume that there are no correlation between prime numbers. Sorry, so this is prime number. So if there are no correlation, of course, this is a great assumption. 1 over p is essentially the probability that if I take a random number x, this guy is divisible by the prime p. So what I've done here is turning a deterministic statement in a probabilistic one. Because it goes without saying that along the sequence of natural, each 3 of them is divisible by 3. Each 5th of them is divisible by 5, and so on and so forth. Okay? So this is deterministic, what I just said, but I just turn it in a probabilistic statement. Namely, if I pick up a natural numbers, what is the probability that is divisible by a prime p? 1 over p. Okay? Now, assuming so, if I ask, what is the probability that x is a prime? Well, should not be divisible by 1 half, by 2, sorry, and the probability is 1 minus 1 half. Should not be divisible by 3, and the probability is 1 minus 1, 3, and so on and so forth. So roughly speaking, the probability that x is a new prime number goes like this. Now, working with infinite product is pretty complicated, but I can turn immediately into a sum, because if I take the log of this quantity, the product becomes the sum, and p is already larger than 2, so I can develop the logarithmic truncated to the lowest part. So the logarithmic of omega x is essentially given by this sum. But then you say, but what you have done, you don't know the prime, what it is, so how you can sum the prime? Here is the coup de théâtre. The coup de théâtre is I can convert this sum on prime into a sum which involves the integers with the probability that the integers are the prime. And this is the same function I'm talking about. At this point, I immediately got a differential equation. So if I differentiate left and right, I got this. And what is the solution? 1 log x. So the probability that you find a prime is 1 over log x. And therefore, the number of primes up to x is the probability times the interval. And it goes like this. Okay? And now you see that the scaling I was giving you before, the n prime goes like n log n, is just the inverse at the first order of this function. Okay? Now, observe one thing, that prime are rare, we know it, but after all, not so rare, in the sense that their numbers is larger than the square. Indeed, the number of primes we just count now goes like x log x. But if you think the number of square goes like square root of x. So in any interval of natural numbers, you find more prime, actually square root of more, than the square of them. Now, if I compare the actual formula, namely the number of prime less than x, which is this one, with the difference of the Gauss approximation, you see that I mean, there is substantial error, which roughly speaking, just counting the number of digits here and there, goes like the square root of the number. Okay, so the absolute value goes like square root of the number. Now, the question is, can we do something better? Can we refine the Gauss approximation? And this is where in the story enter Riemann. So let me just tell you what is about the Riemann. So Riemann, with long and very, very interesting reasonings that you can find on a beautiful book on it's called Riemann Zeta Function by Edwards. The first pages is devoted to this problem. Say, look, the function which count the prime, as a matter of fact, can be approximated by one function which is given by this. It's an infinite series which involves the logarithmic integral as before, but now is alternating because this coefficient mu n is an arithmetic coefficient which is called Möbius coefficient, which goes like this. If the number n, the natural number n, is divisible more than twice than a prime, like 12, 12 is 2 times 2 times 3, so mu of 12 is 0. On the other hand, if n is square-free numbers, means contain only one prime in the decomposition, it just count how many prime factor you have. It's essentially like a fermionic numbers. You can treat the primes as a fermions. You can never put two primes on top of the other, according to this interpretation. And if you have an even number of fermions, the fermionic number is 1. If you have odd numbers of fermion, the fermionic numbers is -1. So this series is alternating. And so this is why, at the end of the day, is better than Gauss. So indeed, if you go and now check once again the actual counting, what is the counting given by Gauss and the counting given by Riemann, now you can see that first of all there are some negative and positive. So this function sometimes larger, sometimes is. But what is more important is the size is somehow better of at least order of magnitude. Okay. So if you go and check, so Gauss somehow for long range overestimate the actual numbers. Riemann, on the other hand, oscillated around it. And indeed, if you take the difference between the Riemann zeta function and the actual primes, this is what Michael Berry dubbed the music of the primes. Because this is like some kind of music signal, if you want, okay? And actually, you can even run on your Mathematica, converting in sounds, even though it's not very pleasant, I can anticipate to you. So, what Riemann does is, this is the best approximation of the continuous function. But the function themselves we know as a step function. And so Riemann asks, can I really approximate exactly this function? And this is where the zeros of the Riemann function enter, because if you now add the contribution coming from the zeros, rho are the zeros, the non-trivial zeros of the Riemann zeta function, what you get is kind of Fourier series. So this zero is a real and imaginary part. So let's say this is the actual function which count the prime. This is the continuous part given by Riemann, which is pretty good in the sense it goes up and down. But if you want really to reproduce the steps, you have to introduce the zeros. And more zeros you introduce, more the Fourier series get closer and closer and closer. So if you include them all, you just reproduce perfectly also the staircase of this function. And Riemann says that if all the zeros has a real part equal 1/2, we know for sure this kind of bound for the difference between the actual zeros and the logarithmic of integral, okay? So this is also an equivalent way of formulating the Riemann zeta function. Now, with prime you can go handless. So for instance, imagine I order the natural number in spiral, okay, like this. So I'm doing 1, 2, 3, 4, 5, 6, and I'm growing like this. And imagine I start now erasing all the prime in this sequence. 7, 11, 13, 17, and so on. You might ask, on a gross scale, what's going to happen? Okay? Are the prime accumulating somewhere? What they do? Well, once again, it's a question of scale. So if I do, don't remember how much, 10 to the fourth, this is what you get. But if you really go larger, you see the prime start to have beautiful boulevard in this kind of number town. Okay? So you have really a planar, and you ask where are the primes? Well, they like to be along boulevards here. You see, even long boulevards. These, as a matter of fact, are all the quadratic equations that was well known to Euler. For instance, n squared minus 41n plus 41 generate 82 prime numbers in a row. So in these figures means I have 82 primes which align exactly along the same things. So this picture alone says that it's very probable that you might have quadratic equation which produce a long string of primes. Okay. Okay, so I think we have got enough familiarity and, how to say, curiosity about the prime. Now let me go back to the original problem. The problem is, imagine I have a divisible sequence of integer, of numbers, Sn, as the prime. How can I find this potential Vx I'm talking about? So I want to engineering my Schrödinger potential to have exactly that prime. Now, I can offer two methods. One is the semi-classical ones, and the other one, which is the exact one, which is related to also a beautiful subject of theoretical physics, which is the integrable model, solitonic equation, and this and that. Now, before going into the detail of this method, I want you to think and to consider the following things. Imagine that I've been able really to construct this potential which has the prime as eigenvalues, as I'm going to show you in a minute. So imagine that you know this. Well, if this is done, I can solve essentially with zero complexity the so-called primality test. Now, in mathematics, if I give you a natural numbers, I don't know, 1031 is a prime or not? Now, 1031 you can check easily, but if I start giving you large numbers, the way is a priori, then can be refined, has been found a new algorithm, but essentially you have to check the division of this number through all the prime number up to square root the number itself. So it's an algorithm which is complicated. So the primality test of a number requires certain effort, certain complexity. Now, I want to point out that from physics point of view, if I'm able to construct such potential, primality test is like this, okay? Zero complexity. And the reason is, imagine I have this potential of the prime. So I want to check, say, whatever, a number 1031. First of all, I truncated my potential in such a way that become a potential with asymptotic states. I can always do some knob, I just cut it. At this point, I create a wave with number proportional to the number I want to check. And this guy that knows, of course, the energy level here. And then I send to this potential. Now, for basic property of quantum mechanics, if this energy belongs to the spectrum, the transmission amplitude is 1. So this wave passes through like a bullet, and then you can see all from the other side. On the other hand, if it's not a prime, so it's out of resonance, this guy just bounces back with probability 1. Okay? So I want to say that you might spend, let's say, 1,000 of years constructing this potential, but once you have it, so once you have spent, how to say, the industrial time to construct it, at this point, all the primality tests from there on, it's just question of zero complexity. You just send it through. I will come back this to the last part of the talk, to comment more. Now, let me go to the methods to construct such potential. Now, the first method I employed is the semi-classical one. Now, semi-classical was the formula worked out by Bohr, by Sommerfeld, and become kind of a very sophisticated set of technique. In particular, says that the integral of momentum time the coordinate on a closed orbiter has to be equal n times the action, the Planck action. Now, what is not well known is that this formula, you can invert it. So what I mean is, all of us are very familiar with these kind of things. And for instance, if I give you a potential, I don't know, square root of x, so I do 4 times like energy minus the potential here equal ny, and then getting through, you get the energy as a function of the quantum number to some power. So you can spot out the... So this is the usual use we do of the semi-classical formula. What I'm saying is this formula can be inverted. Namely, I can ask what is the potential which provide me some given spectrum. And so this is what I've done in already long ago, 1995. So this is the formula which give you the potential as a function of x, so the inverse function in a way, given in terms of the density of states of the problem. Okay, so if you give me the density of states of the problem, I apply this formula, I get x as a function of v, and I invert it. A simple use of it. If I take the harmonic oscillator goes like n. Therefore, the density of states is constant, is 1. I have to integrate square root of this. The square root is v, square root of v. And therefore, square root of v equal x means v equal x squared. Okay? So this is how it works, this formula. So I employ the density of states. Now, the density of states, this story is fantastic because out of 2 ignorances, you get something. I told you that there is no closed formula of the prime. So you say, how the hell you can find a potential if you don't even know the primes? Yeah, but this formula employs the density of states. The density of states, I remind you, is how many levels you have varying the quantum number. So it's something like d over dn. But we know from Leibniz that the derivative of an inverse function is the inverse of the derivative. So this is 1 over dn over d. But this I can get from Riemann, because the inverse function I know of the primes. So out of 2 ignorances, I got the density of states, the inverse of that. So I plug in, and then I compute the potential, simply like that. And the potential looks like this, okay? So this is really numerically exact, how to say, I'm just plotting for certain range, and asymptotically, it goes like x squared log of x. It should be, because x squared give us as potential n, and log x give log n, essentially. So this potential asymptotically reproduce the large scaling limit n log n. Of course, I can take seriously this potential. Then I plug into numerical diagonalization and see how good the result of this potential compare with the prime themselves. And so this is a kind of comparison up to 1,000 numbers. And essentially it's pretty good in the sense this potential, remember that the prime number function was something like this. I'm exaggerating. Now, this function, of course, has a continuous function. And essentially, what I got with this formula is not the eigenvalue, but when this happened. So when this happened, when it passed through this one. Now, sometimes it might happen that it really passed for the prime itself, but you should expect in average to be between two primes. Sometimes closer to one, sometimes closer to the other one, sometimes far, especially if this interval is very large. But this is the best you can do through this continuous function. And you see, I mean, after all, the result is not so bad. I mean, compare pretty good with few percent of error. Now, let me go to the exact realization of the potential. So now the thing is not that I want to have a potential which has semi-classically the spectrum of the prime, but I want a potential which has exactly the spectrum of the prime. And this can be realized experimentally by laser. This is what we have done with the work of Donatella Cassettari. And so this is what justified the title of my seminar, namely, we have been realized an holographic realization of this prime number potential. Namely, there are some space laser modulator, so it's also called, I think, speckle, which provide the Fourier transform of the light. So essentially, I compute the potential, I made a Fourier transform, Donatella is able to do this Fourier transform, and when you shot the light on this, produce in a space, in a region of space, a trap, an optical trap, which has exactly the levels I'm looking for, okay? And then you can insert in this potential atoms, either boson or fermions, and you can do a lot of physics with that. So what we have done essentially is a quantum abacus. So some very simple device, which however contain all the ingredients to do arithmetics in the usual engineering sense of the word. So how to do it? So theoretically, the tool we use goes under the name of supersymmetry quantum mechanics. Now, what is supersymmetric quantum mechanics? Is the following. If I have a potential with certain energy levels, through a transformation, which is called supersymmetry, I can associate to this potential another potential which has all the energy level of the previous one but the ground state. Okay? Now, this is the idea. Supersymmetry allows me to do this map, but then, of course, I can go on. I can start from this potential and associate another one which has all the energy level but this one, and so on and so forth. So, in a nutshell, by supersymmetry, I have a sequence of potentials which one by one depleted always the lowest energies. Okay? Now, what I've done is I have engineering back this procedure. So, you give me a set of numbers, these ones, I promote it to be spectrum, and then at this point, I have a way to first starting from this and spotting one potential which has this guy as eigenvalues. Then reversing the story, I will have a potential which has these two guys as eigenvalues. Reversing the story, I have another potential which has these three, and so on and so forth. When at the end, I accommodate them all, okay? So this goes through the solution of a recursive differential equation of Riccati type, where enter the energy I want to accommodate, and then this potential, which is computed along the way, and this function f, which in technical language is called the superpotential. So if you solve this recursive set of equations, at the end of the day, you get the potential. Now, imagine you are curious to know what is the potential we accommodate exactly the first 40 integers. A priori would say, okay, take the harmonic oscillator and cut to 40. It's not true, of course, because when you cut, you alter all the story. I want exactly to have 1, 2, 3, 4 as a spectrum, and this is what you get, okay? This is the final potential, which has exactly the first 40 level of the harmonic oscillators. Now you see there are oscillations here. The number of oscillations is something essentially proportional to the number of levels you are putting. Although, if you take the average of this potential, you get exactly the x squared. So it's some jiggle around the x squared term. Now, if you do for prime numbers, let's say for the first 45 primes, this is what you get. This is exact. This is an exact potential, which if you diagonalize by numerics, by whatever, is exactly the first 45 primes. Now, if you start going higher, of course, this potential has a lot of oscillations, and which can be a problem. Can be a problem because to realize by laser, you should have a resolution of the light able to resolve these peaks, okay? So this is what has created for us a lot of problems to really set up in lab some explicit potential, some really laboratory potential, which set up certain number of primes. Namely, you should have laser resolution pretty high to resolve it. What you could do is something approximated. Namely, you know that if you have a function, the best way to approximate by power is not use the naive polynomial, but just use the Chebyshev polynomial, which is the best way of approximating a function by polynomial. So in this way, I use just the first 30 Chebyshev polynomial, and this is what I got as a result. So comparing the eigenvalues of this Chebyshev with the primes, well, I mean, it's not exact, of course, but there is certain resemble with certain variation, it goes without saying. And then if I increase the number of Chebyshev, I say Chebyshev because in lab Chebyshev are very easy to realize, okay? So then you get another sequences which, I mean, it's not, of course, the prime themselves, but the difference start to become lower and lower. Now, so this is what we have done in lab. And as I said, you can do a lot of beautiful physics of it. So imagine you have this trap. Imagine you want to study, for instance, transition between primes. What you do, you just shake it, the potential like this. You make the laser vibrating with time, and the vibration is what induce jumps. And then you can do a lot of physics, both with fermions, where when you put it, they start to accumulate all the primes, or with bosons, which are all in the ground states. But you can do also a lot of other problems associated to arithmetics. So let me just spend the last minutes of the seminar illustrating you what you could do. Now, factorization is well known. Factorization is given a number which is not a prime, that you have checked with this machine. It's not a prime, so you want to factorize. Well, you can use the same kind of idea to sort it out, an algorithm, which is not like the Shor algorithm. In computer science, the factorization is addressed from a software point of view by the so-called Shor algorithm. This device addresses the factorization from hardware point of view, because construct really a machine which does exactly this with the minimum number of complexity. Now, this, as I said, require a special seminar in itself. I don't want to go. I want to now illustrated you probably a less known topics, which is lucky numbers and Goldbach conjecture, just to illustrate what you could do once you have such machinery in lab. Now, what are lucky numbers? Lucky numbers was invented by Stam Ulam. Stam Ulam, you know, was a great mathematician, also involved in Manhattan Project. He was what designed really the computers in Los Alamos and this and that. He was very enthusiastic about number theory. And he defined the lucky numbers in this way. I told you that in general, in number theory, you can select certain sequences by certain sieve. So you have to just give me the rule, okay? Now this lucky number, the sieve of this lucky number is very similar to the sieve of Eratosthenes, which we saw before. However, eliminate time by time number based not on their original position, but instead of what has been left. So let me illustrate how it's done. Imagine I take the sequence of all the natural, okay? Remember, prime number is start from here, select 2, and then kill 4, 6, 8, blah, blah, blah. Then you go next, select 3, and then you kill 6, 9, and so on. You see, when you kill 3, you are taking 3 times the position of these numbers, okay? But the numbers are rigid. What Ulam did is take the sequence of integer and eliminate the 2 as before. Well, after the first step, you are left out with these sequences of odd. Now, the point is the next number is 3. Now, the rule is you eliminate 3, but as a position of this new string, not of the previous one. So 1, 2, 3. So I eliminate 5, okay? Then I have to 1, 2, 3. I have to eliminate 11. So the next step, you eliminate 1, 3. Now 5 is gone, 11 is gone, and so on. What is the next one? 7. Now you have to eliminate 1, 3, 1, 2, 3, 4, 5, 6, 7. I have to eliminate 19. Okay, clear? So each time that I kill the number, I squeeze them out and then reorder them. And the position was not the 6th position, has changed because they were whole. So he called lucky numbers because what survived this, in his opinion, were really lucky. Because survive an infinite, many sieve at the same time. So this is the sequence of the lucky number at the end of the day. It's endless series according to this sieve. And these numbers are really cousins of the primes. For instance, their density goes like x log x, and so many other properties. Now, you might ask, can be lucky numbers which are primes? Well, you spot many. 3, 7, 13, 31, 36, 47, and so on and so forth. And then you can ask many other questions. Now, this question I just posed, are there lucky numbers which are also prime? With our device, can be immediately solved because I can construct with the same token a potential which has the prime number as eigenvalues, a potential which has the lucky number as eigenvalues, and then I send a wave proportional to the number I want to test. If it's a prime, pass through here, and it's a lucky, pass through also there. And then you just observe where are the peaks of the transmissions, okay? So very simple. I want to say at the end of the day, the quantum abacus allow you to solve this problem in really 0 time, in a way. Now, Goldbach conjecture. Historically, this is due to a letter of Christian Goldbach to Euler that say, but it's really true that any even number can be written as a sum of primes. Now, at the first sight, you might be surprised. Say, how come? I mean, the primes are so rare. But then when you start doing, you realize that there is typically not only one way, there are many ways. For instance, 28, you can write like 5 plus 23 or also 11 plus 17. And this is true for all. So it seems that not only is possible, but there are many, many ways of doing it. Actually, as a physicist, we can immediately estimate this. The reason is, imagine I put the primes here and here, so I put here up to the 10th prime, and here I put the sum of them, okay? Now, this matrices goes up to 29 plus 29, which is 58. But imagine I spot the number less than the highest one. So how many there are? These are those which are above this diagonal. But then there are a lot of repetitions. So for instance, 18 is here and here, here. So how many there are really which are never repeated? Just these quarters. Okay? So how many numbers there are in this quarter? Well, it's exactly a quarter of this square. So the number of sum less than x goes like n squared divided by 4. But we said before, the number of primes up to n, up to x actually, goes like x log x. So this number of sum, if you give me the integer x you want to know, the upper bound, as this kind of terms. But how many even number are less than x? They are linear. So you see, there is a huge possibility to be filled in these ones. For instance, if I tell you I have x equal 10 to the 6, how many possible way I can write down the even number below 10 to the 6 in terms of primes? Well, the number of sum is astronomically, goes like 10 to the 9th, and the number of even is 10 to the 5th. So there are astronomical way of getting this one. So it has to be an enormous degeneracy. Indeed, there is a formula which computes this degeneracy. It goes like the name of Hardy-Littlewood formula. The degeneracy is proportional to the probability of these two primes. But then you have to correct with some terms which get in account the divisibility property of the number itself. So at the end of the day, this is the degeneracy that you get for representing an even number of x in terms of primes. This is a universal quantity. It's called Hardy-Littlewood formula. And if you plot it, this is how the degeneracy of this level. So if you give me 60, you have if you give me a number here, I don't know, 1,000, very, very close, because depend very much on the divisibility of the number, you have from 20 times up to 80, 100 times to represent this sum. Okay, so there is a huge degeneracy. Now, physics-wise, so this is mathematics. Physics-wise, the story once again turns out to be very simple. I can construct in lab with the same token of potential, which has the prime, along x, the same potential along y, which has the prime, and then I can add. At this point, the two-dimensional potential become this, pretty ugly, pretty crazy, because there's a lot of holes. Nevertheless, this potential, if the Goldbach conjecture is true, must have the spectrum of the harmonic oscillator. And you can check, as I say, you can do the transition between them and observe if you miss some of them, if there is no levels that you can go with. Okay, so let me just go to the conclusions. As I say, there are very interesting interplays between number theory and physics at various levels. Level of combinatories, partition function, quantum mechanics, statistical physics, and so on. We have given essentially what is called in physics proof of principle, namely that it's possible to realize in lab quantum mechanic potential which encode interesting arithmetic sequences. Can be done, this is what I want to say, and we did it. And these realizations, at the end of the day, transform genuine mathematical questions like primality, factorization, intersection of a lucky number with primes or whatever else into quantum experiments. And therefore, these quantum abacuses provide an alternative way to implement quantum algorithm, because the usual frame is through software, which of course is not immune by error and other stuff, but this way of doing provide really a hardware way of addressing a specific question. Okay, and with that, I leave it to you, and thank you for your attention. Wait. Dimitri, give the microphone. I cannot hear. Or speak loudly. Speak loudly. Well, this potential accommodate the twins. Yeah. You are asking, can I construct a potential which has only the twins?
Yeah, because
Yeah,
it's going
I
to
can.
grow faster.
Absolutely, I can. Yeah, in principle, I can. So she's asking, no, prime says the tendency sometimes to have two of them that differ just by two, like 17, 19, 29, 31, and this. So they are like this. Other time are well separated. By the way, this is the reason why this potential is crazy, because these levels are not regular, right? Sometimes they are very close, so you need to have a potential which is small enough to accommodate near like this, but sometimes very high, so need to be very steep. So this creates all these crazy oscillations, because you want to accommodate numbers which has this Dr. Jekyll, Mr. Hyde behavior. So sometimes are smooth, sometimes are crazy. Yeah. Yeah.
Well, very nice talk. I really enjoyed that. So two things. One is I'm curious about the eigenfunctions.
Yeah.
Have you looked at the eigenfunctions corresponding to? Well, do they have any special properties? Have you plotted them? Do they have any shape that we can recognize?
Not really. I mean, we know Liouville theorem which say if you have a potential which has an increasing number of eigenvalues, the corresponding eigenfunction has an increasing number of nodes. They satisfy all of them. There are some little structure associated to this oscillation of the potential, of course, but not particularly, at least not what I saw. So in a way, I saw what I was expected to see. You see, consider one thing though. If you give me a sequence of number admissible, I can find for you an Hamiltonian. But the Hamiltonian is not unique. I can find infinitely many Hamiltonians, which has that spectrum. So the spectrum is the same, but each Hamiltonian is their own set of eigenfunctions that therefore can become as crazy as you like. I mean, crazy in the sense different as you like, because the general principle hold for them as well.
Yeah.
Yeah.
That relates exactly to the second part of my question. In density functional theory, we have a theorem that states that the ground state density uniquely determines the single body potential.
Yeah, it's true.
That's
also
the ground
here.
state. Exactly. So if one combines this with what you have, one can look at what's the ground state density that produces, through density functional theory, the potential that through your theorem produces the prime numbers. So you have a density distribution which by mapping these two theorems generates all the prime numbers. Have you looked at consequences or anything of this nature?
So this is indeed one of the things which always stun me. Namely, is it true, as you said, that one function, the ground state, contain all the information about the primes?
Yes.
Is it true? So this means that there is one function which is even smooth that contain them all.
Yes.
Now, obviously, finding this function from basic principle, I didn't succeed. But it's fascinating to think that there is a smooth function which has all the information on the primate at once.
Yeah.
I would like to to have it.
Okay, there are two of us.
But it's like this. Yeah. Okay. Actually, the way you can also do experiment with these things is once you prepare it something, you release the trap, and so they start moving according to the density, the modulus square of the wave function. Yeah. Therefore, if you compute a wave function theoretically like this, you can make some experiment to flight of time, and so making all the things to observe where the atoms were somehow. So you can make use of this wave function together with the eigenvalues as well. So it's an important information on the problem. Yeah.
Okay.
Yeah.
Thank you. Okay. Well, I have another thing, but if there are other questions, well. Well, I'll pass it to you then afterwards. One simple thing, I was confused about your quantum test for primality.
Yeah.
Because in mathematics, what we call the spectrum is the list of eigenvalues. But in physics, what we call the spectrum corresponds to the differences between eigenvalues.
No.
So when you put the light and shine through, you'll get the transitions, and the absorption, on the other hand,
No. It's not true. No.
Okay.
So I have to fix, of course, a ground state.
Yep.
So indeed, even semi-classically, my formula is a constant.
Okay.
So I have to adapt this constant such that I get 2, 3, 5, and not say 2, 4, 6. I mean, this is okay. This been said.
Okay.
But what you are doing is if you shine line on something to induce transition. But in this case, you can do this just shaking this guy and let allow. No, here I just scattering process. So instead of light, I can make particle hitting on this potential. And once you have a potential, you see, it's not transition that you are computing, but you are really computing. So imagine that you have a potential like this. You can compute the T of E and reflection of E, but not difference of E. I mean, once you have chosen everything, it's given. I'm not. So at this point, I can really make things like this and see whether this guy has some specific peak somewhere. Yeah. Okay. Here not, but if I do vice versa, if I do some bound state here, so when I hit a bound state, this guy has really a peak. And the reason is when I enter here, the number of waves is exactly the one of semi-classical, so it's a resonance. And then the particle get through.
Okay.
Why? If they are detuned, I mean, I made it sharp in the sense t equal 1 is never t equal 1. It's something like, instead of being delta function, it's something like this. So there is a teeny interval in energy where this guy jump. But it's E, not the difference of E.
I understand that in the scattering scenario
Absolutely,
you're describing now.
Scattering.
When we think about an optical scenario where the transitions are differences, then they are differences with regard to a fixed reference state that you have chosen.
It's true. No, but here I'm thinking really scattering.
Okay.
So I can think really particle, if you like. I mean, so not inducing transition, but just checking the spectrum itself.
Okay,
so,
thank you.
Yeah.
Well, first, thank you for the lecture. It brings me many thoughts to think about in quantum mechanics. But my question is related to the symmetries that you could find in your system. Could you say something about it?
Yeah, well, I mean, roughly speaking, the only symmetry which I enforce, but was more for utility, how to say, just for simplify the problem than something basic, is Z2 symmetry. The only thing I've been using, because I have essentially one-dimensional potential of quantum mechanics. So the best it could happen is Z2, but I cannot have any other crazy symmetry. But this, once again, I want to stress, is not something fundamental. It's something I used because it's much simpler to find the spectrum of potential, which is Z2 symmetric, rather than spectrum of potential, which is crazy shaped. Okay? Because as I said before, given a spectrum, there are infinitely many potential which support that. And I found among the infinitely many potential, the only one which is Z2 symmetric. But just for, how to say, for simplified, even the graphics. But nothing fundamental about that, yeah.
Okay, I have a maybe final question. So you didn't speak about factorization, but do you already have a machine that can break passwords?
Yeah, I mean, the point is, I mean, we are setting now the things, so probably in short time we have a paper out of it. The idea is the following: the typical algorithm that address factorization are sensitive to the digit of the number. So the complexity grows with the digit of the number. So if you have a number, such a digit is much more complex than a number is like this, okay? However, this is not really the sense of the story, if you think, because a number like this can be prime, so nothing to factorize. Why? A number like this might be many, many primes on it. So I want to say the actual complexity of a number is related to the numbers of factors, not to the number of digits. Okay. Now, that being said, we set up a mechanism which use the minimum amount of complexity to factorize the number, which is equal to the number of factors. Okay? So it doesn't use Shor works on the digit. We work on the factors themselves. And therefore is a priori much more convenient way of doing it. Now there is a catch, theoretical and experimental catch. The theoretical catch is, okay, assuming that you are right, so you are saying that you are much better than Shor. In principle it's true, but the price I have to pay is that I have to design this potential. Okay? So you might ask, yeah, what you gain this, it takes you the age of universe to construct this potential. So what are you talking about? No, there is a very important theorem of computer science that's saying solving the equation I have to solve require scale exactly like the number of operations that Shor has to do. So we are exactly the same complexity of Shor, not much worse, but once we have done, we are better. Okay? Now, this is theoretical. The bottom line is, and this I found extremely profound, I mean, and the bottom line is, in mathematics, infinity exists, although it's an idealization. So there are infinite number of primes. If you want to distinguish two of them, you should have a resolution at least of 2, because it can be primes, one on the other, but 2 over infinity. So you should have a resolution which is essentially 0. But in physics, we never have 0 resolution. So I don't know, if you do optical scattering, you might have 10 to the 13, the Rydberg constant. So this means physics always give me a bound, the number of level I can resolve. I can improve it. Might be instead of 10 to the 13, I can go 10 to the 26. But in physics, there is always a cutoff. So I find fascinating that physics can crack hard problem mathematics, but there is a fire back, namely physics has a cutoff, while mathematics none, and therefore you can always crack a certain amount of them, not them all, okay? So it's fascinating, this interplay, even though physics, in principle, you can improve it. There is no obstruction, I want to say. Yeah, but reality is much more complicated than that. Okay.
Okay, so stay calm. Your bank accounts are not compromised yet.
Your bank account is safe.
Okay, thank you very much again.
Okay. Cheers. Yeah.